when we have anything in our integral that looks like this, okay, these look like pieces of rules that we've seen before, but not always are they going to be the straight up rule. Like the inverse sine rule would be like 1 over this, right? But not always are we going to have this 1 over the square root of a squared minus b. Okay. Sometimes we're going to have these inside of our integral, and we're going to need a method to do the integration. Sometimes we can do it just fine, like maybe there's a u du substitution we can do, or maybe it's an inverse trig rule, or maybe not. Okay, so what we're going to do is we are going to use our knowledge of trigonometric identities and our knowledge of triangles to do what we call trig substitution. Okay. So these three are going to be the biggest that we use. And I don't really know why we have to rewrite the second one to be the third one. Because we have the second one, we have the third one. But there's a reminder. The book wants you to really remember it. Okay, so for u du substitution, we said u equals something with respect to x. U equals x squared plus 5, or u equals 15x minus 32, or we picked something inside of our integral and set it equal to u, and then made sure the derivative of that was also in our integral. Okay? What we're going to do for trig substitution is we're going to set x equal to something. Okay? So, first, let's look at the case where we have the square root of a squared minus u squared. Okay? If we let u equal a sine of theta, okay, why would we do that? Okay. If we let u equal a sine of theta, well, first of all, the sine of theta would be u over a. So we could draw a triangle where opposite over hypotenuse is our ratio of u over a, right? Okay. And that would make this side square root of hypotenuse squared minus leg squared, right? Okay. So why is this beneficial? Well, if we have the square root of a squared minus u squared, okay, the book uses u's. You can also think of these as x's, okay? Then if I let u be a sine of theta, gosh, I really don't like what they're using u. Are you guys going to have a problem with me changing all of these to x's? I think this would be better for us. Yes. Okay. I try to take a shortcut and not have to type this all out myself when I just use the book page, but I really like x's. Okay. So.
Does it have to be axis can't be binomial term?
Well, and see, that's why it could be a binomial term. Okay. But for right now, let's just work with x's, and then tomorrow we can worry about the binomial case. Okay. So the book does this because it doesn't necessarily have to be x squared. It could be, 4x squared or whatever. But we'll just keep it simple for right now. Okay. So if x is a sine of theta, then x squared would be a squared sine squared theta. And what happens? We can factor out an a squared. And so this is really a squared times cosine squared.
Is theta a variable or considered known?
A variable. So basically, we're taking our integral and we're changing it from with respect to x to respect to theta. Okay? So wherever you see this, we're going to change it to a cosine theta. And then anything else in our integral, we can change according to this substitution right here.
Does that affect our indexes too?
We're going to worry about that tomorrow, but yes. Okay. Right now, we're just going to focus on the integration. Okay? How about a squared plus u squared under our radical? What would be a nice trig identity that would work with a squared plus?
Are we taking photos of the board with Kathy?
I'm recording this right now. Because remember, I wanted to do it all on that board.
Yeah.
But we're just going to have to scroll down on the page. Okay, so if I let x be a tangent of theta, then you can see that x over a would be tangent of theta, and we can set up this triangle where opposite over adjacent is x over a. Okay, and then our hypotenuse with the Pythagorean theorem would be the square root of a squared plus x squared. Okay. So if we let x equal a tangent of theta, then that means that our a squared plus x squared would become the square root of a squared plus a squared tangent squared.
Tangent squared,
Which would be the same thing as a squared secant squared theta, which is a secant theta. So anywhere there was a square root of a squared plus x squared, you would replace it with a secant theta. And if there were any x's floating around, we would change them to a tangent theta. And then our last scenario would be the square root of x squared minus a squared. So if we have the square root of x squared minus a squared, what we can do is let x equal a secant theta. In that case, x over a is secant theta, so you can see here that we have hypotenuse over adjacent is x over a, and then we can use the Pythagorean theorem to get the third side of that triangle. So then when we do our substitution, x squared minus a squared would become a squared secant squared theta minus a squared, which is a squared times secant squared theta minus 1, which is a handy-dandy trig identity. A squared tangent squared theta. So it becomes a tangent theta. Okay. Now, you would not necessarily need to memorize everything that I have in green. Okay. because this is something that you could reproduce without having to memorize it, right? Just using our knowledge of identities. However, you will need to remember which substitution is going to be helpful. Okay? Drawing the triangle is going to be important. Okay? For when we get to the end, we're going to want to change everything back to our x's. If you get an integral with x's, your answer needs to be in terms of x. Okay? Well, we are going to change our integrals to thetas. Is what's going to happen. So when we get to the end, we're going to need this relationship to figure out what all of our thetas mean. Okay? So what we're going to do is we're going to do a rule that we already know. We know what this integral should be. It's going to be a very simple integration. That way you can see how everything plays out. Okay?
It's still gonna take a long time. You said today was gonna be.
Yeah, we're probably going to go no.
For just this one interval?
No. This one is going to be short. We know what this is. Okay. This is going to be arcsine of x over 4. Okay, so just keep that in the back of your mind. We do not need to do trig substitution to get this integral. But we're going to do it so we can see how everything plays out. This is a nice simple one. Okay? And if you forget the arcsine rule, okay? So, since we have the square root of 4 squared minus x squared, we can let x be what?
K sine theta. 4 sine theta.
Okay? We could let x be 4 sine theta, which means dx is what? 4 cosine theta. Okay? In order to be able to do the substitution, we also have to replace dx with something. Right? Just like we do with u du. We have to replace u and du. Here we're going to replace x and dx. Or same thing with as in u du substitution. Okay? Before we do anything else, we're going to draw our triangle for reference. If this is theta, we know that our sine ratio is x over 4. So opposite over hypotenuse is x over 4. And we can clearly see that this side would be 16 minus x squared. Okay? So now, what we have is the integral. Dx becomes 4 cosine theta d theta. And we have 16 minus x squared. Now, after doing a few of these, you're going to be able to figure out what this is going to be, right? So you're not always going to necessarily have to go through this step every time, but this is going to become 16 times 1 minus sine squared, right? Which is really just what? So our denominator becomes 4 cosine theta, because this is 16 times cosine squared. So what are we integrating? We're integrating 1 d theta. Which is what? Theta plus c. Okay. We started out with an integral with respect to x. Our answer needs to be in terms of x. So here is theta. How do I write theta? Okay. Well, we know that x is 4 sine of theta, right? So we know x over 4 is sine of theta, which means theta would need to be the inverse sine of x over 4. See how that works? There it is. Now, if you can remember the arcsine rule, I would. Okay. That was a lot of work we did for that one. Okay. But now we have one under our belt. Okay. Questions about anything we did before we move on?
So the only thing that we need to remember is like for whichever things that we're given, what actually.
Because everything else we can do based on previous knowledge.
Are all of them going to end up being one?
No. Just this one because it was the inverse sine.
Oh, okay.
Okay, so now it's x squared minus 2 squared. So what would we want x to be? We want x to be 2 secant theta, which means dx is now, what's nice about this is we have dx and we just replace it with whatever we have there. We don't have to do any funky rearranging, right? So that is what makes this substitution nice. Okay, now we'll draw a triangle for reference. We didn't really need it in the last problem, but we might need it here. So our secant ratio is x over 2, right? Since x equals 2 secant theta. Our ratio is x over 2. So we have x over 2. And so then this side would be x squared. And here we go. We have the integral of the square root of x squared becomes 4 secant squared theta over x is what? 2 secant theta. Dx is 2 secant theta tangent theta d theta. See, isn't that nice? Okay, so right now it looks messy, but to me it's nice to just replace dx. Okay. All right, so let's talk about this right here. This is the same thing as, I'm going to try to save room. This is the same thing as 4 times secant squared theta minus 1. And secant squared theta minus 1 is what? Tangent squared. So let's rewrite that as 2 tangent theta.
Can you just cancel the secant in the denominator, or the 2 secant theta in the denominator with the 2 secant theta in the denominator?
Yes.
Tangent squared.
Okay, so yes, these two cancel, And we are really just left with 2 tangent squared theta d theta. Do you see now why yesterday was maybe imperfect?
Just a little.
How will we integrate tangent squared?
You should use a rule. Okay.
Let's find our cosine squared. Oh, okay, yeah.
Right? Because we know secant squared, we know it's antiderivative, don't we? So when we perform this integration, we get 2 tangent theta minus 2 theta plus c.
And you have to,
All right. Now this is where it gets fun, okay? I have 2 tangent theta. We drew a triangle. What is the tangent of theta?
radical x squared minus 4 is
Okay, here's theta, opposite over adjacent. The tangent of theta is radical x squared minus 4 over 2. Minus 2 times theta. We know theta, well, we know x is 2 secant theta, right?
inverse secant.
So x over 2 is secant theta. To solve for theta, we have to perform the inverse. So this is secant inverse of x over 2. Well, I guess I shouldn't get too excited yet, right? Because we can simplify this a little bit to be the square root of x squared minus 4 minus 2 secant inverse of x over 2 plus c. Pretty sweet, right?
That is something that this is used? Application?
Well, I can name off a lot of things that integrals are used for application.
They use integrals, like does trig pop up in integrals a lot in those applications, or is it more?
What's the radical of?
Well, we're not necessarily using trig integrals. We're using integrals that we're using trig substitution for. Okay. Just for you, Jared, we're going to do an entire day of applications.
Yes.
Of all of this stuff.
Come on, Jared.
Why are you complaining?
It would have been regardless of what it said.
Should be like, thank you, Jared. You are a big
This looks
Hey,
like
yeah,
another
it's-
one of our English.
It's that one.
Well, not quite. We're missing a negative sign.
The one where there's the x times. It's out of here. Arc secant.
But doesn't this have to match this? Yeah. I was going to say, it's not going to work out. for you.
Multiply it by 2 over.
No.
But then you have to, I don't know.
Not yet.
I
Okay.
know
Not close enough.
There's a family resemblance.
Okay, so what's different about this one?
It's plus.
Okay.
it's u is not just x.
Okay. So let me rewrite this as the square root of 2x squared plus 3 squared dx. So instead of, okay, what's the trig function we want to use?
Tangent. Tangent.
Okay, because tangent squared plus 1 is nice, right? So instead of letting x equal 3 tangent theta, we want 2x to be 3 tangent theta. Okay? Which means x is 3/2 tangent theta. So there in turn dx is 3/2 secant squared theta. D theta. Draw your triangle. If this is theta, our tangent ratio is this. So what's the opposite?
2x over 3.
Okay, so I would put this as 2x, this as 3, which makes this 4x squared plus 9. Save it for later. Are you okay with my triangle?
Yeah, I'm just trying to remember how you know which one to use.
Well, to solve for tangent, you would divide 3 over. So your tangent ratio is 2x.
Yeah, no,
over
but
3.
like when you like look, I just can't remember which one. Like when it's plus in the middle, I can't remember which one you're supposed to use.
That's just.
Okay.
That's from the notes. I just need to go back.
Okay. Well, my opinion, our only trig identity out of those 3, that's 1 plus, would be 1 plus tangent squared. So, all right, you ready for our substitutions here? X is 3/2 tangent theta times the square root of 2x is 3 tangent theta. So we have so 2x the quantity squared becomes 3 tangent the quantity squared. So 9 tangent squared. And dx becomes 3/2 secant squared theta d theta. So we have to make our substitutions for any x and any dx. Well, the only dx, but you know. Okay. Those cancel, let's get rid of them. Okay. Like I said, you're going to do this enough to where you're going to be able to figure out what's going on right here. This is really not the square root of 9.
It's 3 secant theta.
Okay, so we can factor out a 9 to be multiplied by tangent squared plus 1. Tangent squared plus 1 is secant squared. So in our denominator, this radical becomes 3 secant theta. And I'm going to go ahead and throw this in the numerator so that we're not all over the place here.
Do we need to cancel?
Yes, yes we do. So I'm going to go ahead and put the 1/3 on the outside. This secant cancels out with this secant. And we have secant theta over tangent theta. What? Okay. How'd you get that?
Divided by 3 to see the denominator, make cosine, so it's cosine theta over sine theta times cosine theta, so it's just integral of 1 over sine theta.
Okay, with secant over tangent, you don't have a nice u to u substitution. So we're going to have to use some of those basic trig identities to rewrite it into something that we can integrate.
you get the natural log of cosecant theta plus tangent theta.
Yeah. But negative.
Yeah.
Okay, so we've seen that a couple times now. You probably need to be prepared for the integral of secant and the integral of cosecant while you're doing your homework. They could pop up. All right. Is this how I want your answer? Can you see why I wanted to use the whiteboard? Well, we would. Okay, so here we have cosecant theta. What is the cosecant of theta?
4x squared plus 9 theta.
Okay, so hypotenuse over opposite. Hypotenuse over opposite. Plus cotangent.
Okay, so this is weird. You know, whoever's deriving these so we can integrate them should really just leave them in the terms they get.
Okay. Now, this section has a lot going on. Okay? If you have, the substitution down, awesome. But we have to be prepared for any kind of trig integral that we might see, right? Okay, so first of all, that's why last section was important, because you never know what you're going to get here. And all the roads you know before. So today, I would like you to complete on page 539, 5 through 16, and these are broken up to, these four are all x equals a sine theta. These four are all x equals a tangent theta. These, well, I guess there's probably not broken up in fours, are they? Yeah. That's 12 problems.
Yeah.
Okay, so you have 3 sets of 4 similar problems.
Can you go back to the slide that shows the one with all the triangles on it? The first one where you talks about the useful.
This is only for both.
What page?
It would be probably just a couple pages before your homework. I would try like 537, 536. Let me get my book. It's buried here. Nate Cappy, you can stop it. Page 533 are all the triangles. Did you hear me, Andrew?
Yeah.
Okay.